today, we will introduce briefly the different instruments that we will use for water quality measurements. And then after this, we will go to our instrumentation lab to show you these different instruments. So the first instrument that we will discuss is the total carbon analyzer. And so a brief introduction is it will measure total carbon or total organic carbon. So what is a total organic carbon? It is the amount of carbon that's present in an organic molecule. So let's say you have glucose with a formula of C6H12O6 and a molar mass of 180 gram per mole. So C6 means it has 6 moles of carbon, and if you multiply that by the molar mass of or the atomic mass of carbon, 12 gram per mole, and then divide it by the molar mass of the molecule, you will end up with 40 grams of carbon per 100 gram of glucose, or you will say that you have 40% carbon. Then another one is inorganic carbon, which is basically coming from carbonate ions, gas carbonates, and dissolved gas such as CO2. So the gas carbonates can come from H2CO through carbonic acid, which then dissociates to water and CO2. The total organic carbon is then equal to total carbon minus your inorganic carbon. What is the main source of total organic carbon in surface waters? It's from natural organic matter. And what is a natural organic matter? Typically, we define it as a complex mixture of organic chemicals. It contains low molecular weight acids, amino acids, proteins, and polysaccharides, as well as high molecular weight compounds such as fulvic acid and humic acid. The difference between these two is just their solubility in acidic and basic conditions. And basically, NOM is present in all water bodies because it comes from decaying plant litter. It can come from aquatic life, detritus, and even from the soil and sediment inputs. Thus, the TOC gives an indication of the amount of natural organic matter in a water sample. It is often used as an indicator of the water quality and cleanliness of a water distribution system, as well as water treatment facilities. So if you are to compare between a drinking water and a wastewater, typically a drinking water contains about less than 0.1 to 25 milligram per liter of total organic carbon, whereas if you have a wastewater, it would contain as greater than 100 milligram per liter. And what's the importance of natural organic matter, of determining the concentration of natural organic matter? In wastewater treatments, as well as drinking water treatments that employs membranes, it can cause biofouling of these membranes. And also in drinking water treatments, it can react, or it reacts with the disinfection chemical, the chlorine, to provide or to produce potentially toxic and carcinogenic compounds. So this is how typically the organic and inorganic carbon, or in total carbon, is being determined using a TOC analyzer. First, it is introduced into a furnace where it is combusted completely into a carbon dioxide in the presence of a catalyst, typically platinum. And then it goes into a detector, which is typically non-dispersive infrared. And and then it will give you a signal of in terms of peak, so you can have a peak area. And when you have a standard, your standards will be in the x-axis, it's in milligram per liter. So that's the first part, is the total carbon. When you want to analyze the total organic carbon, the sample is first acidified to less than pH 3, and then sparge gas, either nitrogen or CO2 free gas, is bubbled through the sample to remove the inorganic carbon dioxide before the sample is being combusted. So as mentioned previously, the peak area of a signal is directly proportional to the concentration of the carbon, and it's typically reported as mass of carbon per volume of solution. So this gives an schematic diagram of the inside the TOC instrument. So you have your sample, you have an acid, and sometimes if the carbon concentration is too high, it can dilute your sample automatically, so you have the dilution water. So then the sample is being injected using a syringe. It's injected to the furnace, and then in the furnace is typically, it's 680 degrees Celsius, so your total organic carbon is burned in the presence of a catalyst platinum. Then it's burned into CO2. The CO2 then goes to your detector here. So the next instrument is called inductively coupled plasma mass spectrometry, or ICPMS for short. So ICPMS is typically used for trace metal analysis, and if you compare it with flame atomic absorption spectroscopy, as discussed in the previous lab, ICPMS has the advantage of being more sensitive. It can detect up to parts per trillion level for most elements, whereas the flame atomic absorption spectroscopy typically goes to ppm to ppb levels only. With ICPMS, you're also able to quantify isotopes of element. So when we say isotope, you have the element has different mass numbers. So let's say you have lead. Lead can exist in 204, atomic mass of 204, and then 206 and 207. So those are the different isotopes, and you're able to quantify this in ICPMS. At the same time, the ICPMS allows you to analyze several elements at the same time. Let's say you want to analyze 20, then you can do it with ICPMS, unlike with AAS where you're limited typically to one element each time. So then it offers a very high productivity. So these are the elements. This is the periodic table, and the colored areas that you see here are the elements that can be analyzed or measured by ICPMS, whereas the white ones, either they don't have naturally occurring isotopes, or for example the carbon, nitrogen, oxygen, helium, fluorine, neon. These elements have ionization energies that's either near or higher than the ionization energy of the argon. And this is, later on I will explain that the argon ion is the one that ionizes these elements. But then the ionization energy of argon is around 15 electron volts. So anything higher than this, you cannot measure any elements that have ionization energies higher than this or a little bit near. You cannot measure it with ICPMS. So this is the basic principle of operation of the ICPMS. First, your liquid sample, usually aqueous, is being introduced into the plasma in a suitable form, and that suitable form needs to be an aerosol. So it's a very fine mist of droplets that is you're able to create this through the use of high flow of gas. Then these aerosol droplets goes to a plasma. A plasma is basically a very high temperature where it contains the argon ions, and then the electrons, other ions, and also neutral particles at a very high temperature, 6,000 degrees Celsius. And what happens is that your solvent, let's say water, is totally dried off in this region. Then it dissociates your compounds into atoms and then removes an electron from the components, thereby forming singly charged ions. So the main difference with AES and ICPMS is that with AES, the flame temperature is, for the wide burner, is around 1,200 degrees Celsius, and you are in that temperature, more gaseous atoms are produced than ions. So in AES, we're detecting the atoms. So then, going back to ICPMS, the charged ions are directed through a mass filtering device, and then they're separated based on their mass to charge ratio here, or M/Z. Then the ions exiting the mass spectrometer goes to an detector, which is typically an electron multiplier detector. So let's go briefly to the different parts of the ICPMS, since this is, from all the instruments, this is one of the most complex one. So as previously mentioned, in the sample introduction system, it has a nebulizer and a straight chamber. So wherein the nebulizer creates a very fine mist of aerosols with the help of a high-speed gas, and then this flows over a tip of the nebulizer. Anything that is greater than 10 micrometer is discarded to the waste, while less than 10 micrometer, it can go to the plasma, and it's can be efficiently ionized. So now let's go to the ICP torch and the radio frequency coil, which creates your ions. So basically what happens is there's this gold coil here reacts with your argon gas. So, and in that reaction, electrons are being produced, and at the same time the argons are ionized. So the plasma, as mentioned previously, consists of a highly ionized gas composed of ions, electrons, and neutral particles at a very high temperature, which will then subsequently ionize your samples. After the plasma, your sample goes to interface. Basically, it's just a mass transfer line. So from a very hot temperature in the plasma, before putting it into your detector, it needs to be at least at a lower temperature. So that's one of the reasons why we have the interface. At the same time, also, there's a difference in vacuum from the plasma to the other parts. So it goes to high vacuum. So that's basically the purpose of the interface. Then next we have the ion optics. The ion optics basically transferred the desired ions from the interface region to your mass spec, while it discards photons, neutrals, and the ions or the particles that were not ionized. Okay, then after the optics, it goes through the mass spectrometer, which is typically a quadruple mass spec. And so the ions travel here based on their mass to charge ratios. And then once it comes out the quadruple MS, it goes to another detector, typically electron multiplier detector, where each ion creates basically a discrete electrical pulse, and this pulse is being converted into a signal. So this is a typical result of ICPMS. So on the bottom part, you are able to analyze different isotopes of elements. And on the right side here is an example of a standard calibration curve where you have your standard concentration and the signal count. So then you are able to identify or determine the concentration of your unknown sample based on your standard curve. In summary, this is the schematic diagram of the ICPMS and how it works. So you have your sample that with the use of a peristaltic pump is brought to a nebulizer. In the nebulizer, argon gas also goes in there such that it helps to create the very fine mist of aerosols, and these small aerosols goes into the plasma region. So in the plasma region, once again, your sample is desolvated, dissociated into atoms, and ionized, and then it goes to a interface or mass transfer line, and only the ions passes through the ion optics, and the ion optics guides these ions through the mass spectrophotometer for separation, and lastly to electron multiplier detector. So next is we have a gas chromatography mass spectrophotometry. Usually we call it GCMS, and it's mainly used for analysis of organic compounds, and also it is used for volatile and semi-volatile analytes. When we say volatile or semi-volatile, they should be able to vaporize at temperatures less than 350 degrees Celsius, and this limitation is because of the maximum temperature that a column can go into. So typically you have columns that can go up to 360 degrees Celsius only, and you cannot exceed that temperature. And GC is a standalone technique where you can use different detectors. Let's say flame ionization detector, which basically detects any organic compound that has carbon. And then you have electron capture detector for organic compounds that contain electrophilic elements such as FCl-BRI. And you have nitrogen phosphorus detector, typically used for pesticides. So the first three are more selective, whereas there's a general detector called TCD, thermal conductivity detector, which can be used for any organic compound. So it's non-selective, but also sensitivity is lesser compared to other detectors. So let's introduce first the principle of the gas chromatography itself before going to the mass spec part. So your sample is usually in a solvent, organic solvent, but then it's injected to a liner, which is temperature controlled, and so it's converted to a gas stream. And then there's an inert carrier gas that constantly flows through the column. It can be either helium, hydrogen, or nitrogen, and this carries the sample through the column, as well as during the separation, your compounds are separated based on their affinity with the column as well as with the carrier gas, and also separation is also based on the volatility of your compounds. And then the separated compounds are then swept through a detector. So GCMS, now we combine the mass spec part. With GC, you're able to separate quantify your organic compound. But when you add the mass spec part, you can do both, as well as you can identify the individual components in a mixture. And this is based on the identification of the structure is based on the molecular weight of the molecular ion formed, as well as the different fragment ions. So the basis is for the GCMS is that molecules are ionized into ion fragments at different masses, which are then separated based on their mass to charge ratio. And as previously mentioned, it also creates molecular ion. So the main type of ion production for this GCMS is called electron impact. So basically, what happens is there's a filament that produces electrons, and these electrons then reacts with your compound to produce these positive ions and fragment ions. These are some of the application advantages and disadvantages of GCMS. For analysis of volatile and semi-volatile organic compounds such as organohalides, aromatic hydrocarbons such as BTEX or benzene, toluene, xylene, and naphthalene. There's also ethylbenzene. For example, these components can be found in underground water due to leakage of fuel or solvent storage tanks. Then also polychlorinated biphenyls in drinking water. You can also analyze non-aqueous phase liquids. In addition, you can analyze, let's say, pesticides. But you can also analyze even very low boiling compounds or either very high boiling compounds, but with another preparation procedure, that is, you have to derivatize your sample. And GCMS, the detection limit is typically parts per billion to parts per trillion. So it's usually better than the previous detectors that I've mentioned. So here we introduce the principle of operation of the mass spec part of the GCMS. So after going through the GC module, the separated compounds will then travel into the interface, which serves to transfer these compounds into the ionization source. And then the gaseous sample molecules enters the ionization chamber operating at high vacuum. So here, the sample is being bombarded with electrons or charged particles, as mentioned, resulting in the formation of fragment ions as well as the molecular ion itself. Then these ions and molecular fragmentation products are focused into a beam through a magnetic mass analyzer. The most common one is called quadrupole. Here, the separation is based on the acceleration of the charged particles. So the bigger charged particles are deflected least and travels slower, whereas the smaller particles will be deflected easily and so will travel faster. Then the detector collects and measures the amount of a specific ion. So this is a typical chromatogram of or a typical result of a GCMS. The first top portion is called the ion chromatogram, wherein the x-axis is in minutes, and then the y-axis is the response in the detector. So basically, you see here that if you have two, let's say if you have two compounds, then they are separated. And then, so for each of this compound, it will have a fragmentation pattern. So here they're only concerned with a certain kind of pesticide. So the second figure here is basically the ion or the ion fragmentation pattern. So the x-axis is mass to charge ratio. And then typically they have libraries, so then you can compare your fragmentation pattern to a fragmentation of a compound in a library, and if they are if they have a high percentage of match, then you're able to identify your sample. We move to another very common instrument that's used for organic analysis, and this is called high performance liquid chromatography mass spectrometry. So this is also a separation technique, and HPLC alone is used in the separation and analysis of mixtures of chemical compounds, and once again mainly organics. It is also a standalone technique with various detectors such as ultraviolet, diode array detector, and fluorescence detector. So the basis of separation is you have a column. So you have a column and a solvent. The column consists of your stationary phase, whereas your solvent is called the mobile phase. So when your sample travels travels to the column with the solvent, your sample analytes will have interaction with this stationary phase. So let's say you have a nonpolar phase, normally C18. So if your compound is more nonpolar, then it tends to interact more with the column. So it will stay there for a longer time compared to a less polar compound. So, and then the more polar compound will travel faster with the solvent. So this is what I just mentioned is called a reverse phase HPLC, where your column consists of a hydrophobic packing material such as C18, whereas your mobile phase is hydrophilic in nature. For example, acetonitrile or methanol. And then the reverse of this is called the normal phase HPLC. This is the schematic diagram of HPLC. So you have the mobile phase here. Before it used to be just isocratic, or you can have just one mobile phase, or if you want, you can mix, two mobile phase together, but just put it in one container. But nowadays they have binary or gradient pumps wherein you can introduce 4 different solvents, and you can mix different proportions of these solvents. So in the solvent pump has a built-in vacuum degasser to remove the bubbles, which is unwanted in this high pressure system. And at the same time, it allows the mixing of solvents in the proportion that you want. Then it brings the solvent to the injector. So in the injector, typically you have auto sampler. The sample is being injected there, and then the solvent carries it through your column, which is the heart of the instrument, because this is where the separation occurs. Then it goes to your detector, and then as you can see here, there are different peaks that come out at different times. So that's the result of the separation of the compounds. Now, if we introduce the detector as a mass spec to the HPLC, then it can provide the molecular weights of these separated compounds. And there are 2 main kinds of HPLC-MS. One is the electrospray interface LCMS and nanospray, which are mainly used for polar and ionized compounds. And then the other one is the ion spray LCMS, mainly for non-polar and non-ionized compounds. So the following are the application and advantages of HPLC-MS. It is used for determination of pesticides, polychlorinated biphenyls, pharmaceutical compounds, persistent organic pollutants, PAH, and so on. So very diverse. It can be low boiling or high boiling, it doesn't matter. Also, you can directly introduce aqueous samples, and the only thing is sometimes it may suffer with respect to sensitivity. So usually what you can do is you can pre-concentrate your sample using a technique called solid phase microextraction. And then another thing with HPLC is it uses solvents rather than gas. And sometimes, or more often, these solvents are more expensive and you use more of it compared to a gas, so it's more expensive. So for the analysis of nonpolar compounds, as mentioned previously, they typically employ ion spray LCMS, and the basis of this is so then the sample effluent from HPLC enters a capillary inlet, where once again a nebulizer gas converts it to a charged fine mist in the presence of high electrical potential. Then the fine mist enters an evacuated chamber where the solvent is evaporated, and then it's heated electrically with a capillary, and then the charged molecular ions are produced and then propelled and focused to a mass spec and to the detector. So very similar to your GCMS. And last but not the least is the ion chromatography. Once again, it's a separation technique, but this time it's for the separation of ions, meaning charged ions. It can be inorganic, it can be organic, and the separation is based on the exchange equilibrium between the sample ions and the eluent ions. The anions are separated using a column packed with anion exchange resin, whereas the cations are separated using column packed with a cation exchange resin. And this is the application, advantages and disadvantages of ion chromatography. For rapid and simultaneous determination of anions, to assess the need for specific treatments in water, such as, let's say, for halides, fluoride, chloride, and bromide. For oxyanions, let's say for nitrates, nitrites, phosphates, and sulfates. Remember that excess nitrogen and phosphorus is not good in surface water because it can cause eutrophication or excess nutrients in the surface water, which will cause algal bloom. And disinfection products can be also determined using IC. Example of these are chlorite, chlorate, and bromate. IC is also important in the analysis of special metals with different speciations, meaning they have different charge. For example, chromium, you have 3 and 6, and then arsenic, even iron 2 and iron 3. The method of detection limit is typically 1 to 20 parts per billion level for the said anions. And it uses less hazardous reagents. For example, the eluent is sodium bicarbonate, sodium carbonate, and sodium hydroxide. So, how it operates? First, the eluent is pumped through a system at a fixed flow rate, and initially it bypasses the sample loop. Then, when you introduce your sample, the eluent sweeps the sample into the column, and then in this column, as I've mentioned previously, there's an equilibrium exchange that will occur between the solvent ions and your column, your also your sample ions and your column. And then once it gets out from the column, it first goes to a suppressor, wherein it converts your eluent or your mobile phase into a form that has low conductivity, because the main detector here is conductivity. So remember, let's say if you're using sodium carbonate, sodium bicarbonate, these are also ions. So if you have them in your detection, then you will have a very high background. So the main purpose of the suppressor is to convert this eluent ions into a neutral form, so that there's less background when it goes to the detector. And then the separated ions are measured mainly by conductivity, sometimes also by UV-Vis detector, and also you can integrate ion chromatography with mass spectrometry. So this will increase your sensitivity once again. So that's all. And for the AAS, you should review the PowerPoint on the in the previous lab. So that the last part here is the schematic diagram of ion chromatography, which I already mentioned to you. Right, so thank you for your attention. And then right after this, we will go to the instrument lab, so that I'll show you each of these instruments. And also, since this is really a brief introduction of, various instruments, if you want to know more about this, just let me know, or I believe later on in your next courses, we will be able to use these instruments.